Hello, in this video I'd like to start investigating the second order parts of non-standard models of WS1S. We already know everything that we could know about the possible first order parts of non-standard models of WS1S. We know that they necessarily have to be woozles and that any woozle can be turned into a non-standard model of WS1S. So the question is now, if we have some woozle for our first order part, what possible collection of subsets of that woozle can form the second order part of a non-standard model? And again, our axiomatization tells us a lot of things about, for instance, the closure properties of this collection. We know that it has to be closed under finite modification, union and set subtraction, and also run maps and reverse run maps. And for this video, I'd just like to restrict our attention to the standard first order elements of our models. To show what I mean by a restriction to the omega part, to the standard part, let's consider one of our piecewise periodic models and take the restriction to omega of the second order part. So specifically, we're going to take a set X within the second order part of our non-standard model. I'll call the first order part A and the second order part B. And then we can ask the question, what do we get if we take that set and intersect it with omega? So we just consider the standard elements within this potentially non-standard set. So it could be the case that X is actually some finite set of natural numbers, in which case taking the intersection with omega isn't going to change X. It's still going to be some finite set of natural numbers. More likely, though, this set is going to have some behavior on some finite initial segment of the natural numbers, and then it's going to have a piece, a periodic piece, that starts in the omega part and ends somewhere in the non-standard part. And so if we're just looking at the omega part of this set, it's going to look like some finite arbitrary behavior followed by periodic behavior off to infinity. And again, we're going to completely ignore this bit here. Now, of course, this set here, just when we take the intersection with omega, when we just restrict our attention to this part here, this is not going to be an element of our non-standard model. Every element, one of our axioms is that every second order element has to have a largest element within it. And this set here, it does not have a largest element. And we don't really expect that. Omega is never in any of our non-standard models, and so we can't expect closure to help us here to tell us that X intersected with omega is in our model. Again, the goal here is to start our investigation of the second order parts of these non-standard models by just restricting our attention to what those second order elements are doing over here. We'll answer questions about what those second order elements are doing over on the non-standard part. We'll answer those questions later. But for now, I just want to focus our attention. We take a non-standard model, we look at the intersection of the second order elements with omega. What sorts of sets do we get? Well, in this case, we get eventually periodic sets. So the collection of all eventually periodic sets can be achieved as the restriction of a non-standard model to omega. Could we have a non-standard model that has a second order element that when we restrict it to omega just gives us the collection of prime numbers? Again, this couldn't be all of that second order element. It would have to continue on into the non-standard part so that it had a largest element, and there'd have to be some sort of relationship. We've seen that going into an infinite bit and coming out of an infinite bit, there has to be some sort of relationship between these sets here. In the case of our piecewise periodic models, going into an infinite bit, we had to continue with the same periodic behavior coming out of that infinite bit. It's it's not entirely clear what we have to do with the primes, because the primes aren't periodic. But I'll talk about that later when I talk about the non-standard parts of these models. But for now, let's just ask the really simple question. Can we find a non-standard model of weak S1S that contains an element that when we take the intersection with omega, we just get the prime numbers? And the answer is yes, and there's a very simple argument for it. Here we're setting up to do a basic compactness argument. So we're going to first let T be the set of all true facts of weak S1S. We could, now that we have an axiomatization, we could just restrict this set to be the axiomatization, but we don't have to. We'll then add a constant symbol C to our language, which we intend to eventually get manifested as this set that projects down to the primes. And then we'll add into our collection of statements, 0 is not in C, the successor of 0 is not in C, but the successor of 0, that is 2, is in C, 3 is in C, 4 is not in C, 5 is in C, and so on and so forth. As usual, any finite collection of these statements is manifested by the standard model of weak S1S with an appropriately chosen constant, right? We just take the set of primes up to a certain point, however far this list winds up going. So any finite subset of this collection of statements is consistent, has a model, and so therefore by compactness, the entire collection has a model. So it's going to be some model that satisfies all of the true facts of weak S1S. So it's going to be some non-standard model of weak S1S. And it's going to have an element given by the constant C that satisfies all of these properties. That is, it's going to not contain any non-prime numbers, and it's going to contain any prime numbers. And of course, as far as weak S1S is concerned, this is just some kind of random set. Weak S1S has no idea what a prime number is. And of course, this non-standard model that we wind up getting is also going to have a bunch of other second-order elements in it. It's going to have all of the piecewise periodic sets, because any non-standard model of weak S1S has all of the piecewise periodic sets in it. And it's also going to have a set that projects down to the composite numbers, because the composite numbers are just a finite modification of the complement of this set C. 0 and 1 are neither prime nor composite. 0 is an annihilator and 1 is a unit. But beyond that, if a number isn't prime, then it's composite. So we're taking the complement. Well, actually, we have to do set subtraction on like a infinite interval of our set that projects down to the primes, and then subtracting off 0 and 1 from that set to get a set that projects down to the composites. And there's going to have to be all sorts of new sets in here. When we take our set and run it through various automata, we're going to need runs of that, and those are all going to be new sets. There's going to be tons of new sets within this non-standard model. One of the questions you might ask, this non-standard model that compactness has constructed for us, what does it look like? What does its first order part look like? Well, it can't be omega, because we know that there are no non-standard models of weak S1S. There's only the standard model that has first order part omega. Could it be the case that this model that we construct has first order part omega plus z? Or is it going to have some sort of much more complicated first order part? Well, the compactness theorem doesn't really tell us. It just tells us that there is a model. If we have some sort of set of statements and any finite subset of that collection is satisfiable, then the whole set of statements is satisfiable. But it doesn't really tell us very much about what structure actually satisfies them. We could, if we wanted to, look a little bit more closely at the proof of the compactness theorem, which actually describes how we can construct these non-standard models. But that's really tricky. For now, just looking at the theorem itself doesn't tell us very much about what these non-standard models wind up looking like. The compactness theorem also doesn't tell us much about what the second order parts in this model that it's going to hand us look like. We know that the second order elements are going to have to contain all of the piecewise periodic sets, and it's also going to have to contain this set that restricts down to the primes and all of the things that have to be in that collection due to closure. But it could also contain other sets as well that don't have to be there. Luckily, there is something we can do about that. So let's say that we have a non-standard model of weak S1S. I'm going to call the set of first order elements A and the set of second order elements B. And this could be, for instance, the non-standard model that the compactness theorem hands us and says, here's a non-standard model. The only thing you know about it is that it satisfies the infinite collection of statements that you handed me. And now suppose that we have a subset of the second order elements, and that subset is closed under finite modification, union, difference, and run and reverse run maps. Then I claim that A, along with this subset of the second order elements, is also a non-standard model of weak S1S. That is, we've kind of taken our original model and we've thrown out all of the second order elements that aren't in B prime, that aren't in this smaller collection that's closed under the things that, of course, it has to be closed under in order to get a non-standard model. If we throw those elements out and just have this smaller collection of second order elements, then we still have a non-standard model of weak S1S. So we could, for instance, take the non-standard model that our compactness theorem gave us and tossed out everything that wasn't absolutely necessary. That is, we could let B prime be just the piecewise periodic sets, which absolutely have to be there, and then our new set that restricts down to the primes, and then any set that can be constructed from our new set via some finite sequence of finite modifications, Boolean operations, and run and reverse run maps. Constructing a structure like this that contains a few base things and then contains the minimal amount of stuff that needs to be in there for it to be a structure of a certain kind and contain those base things, those closed under the things that it has to be closed under, is a very common construction throughout mathematics. For instance, one might take a basic ring like the rational numbers and add on a new element like pi or the square root of 2 and want to add on just the very basic elements that need to be there in order to keep it a ring. And this here is a very similar construction. It's just going to contain the few elements that have to be there, and then our one new set that restricts down to the primes, and then only the things that need to be in there because that new set is in there. Specifically things that can be gotten from it by finite modification, union difference, run and reverse run maps. And of course, there's nothing special about the prime numbers in this construction. We could take any set of natural numbers that we want and toss in, using a compactness argument, a set that projects down to that set of natural numbers. We can even toss in many of these sets at the same time. We could, for instance, toss in a new set that just contains the squares, using exactly the same sort of construction. It's just that we'll now add two constants. One for a set that we want to project down to the prime numbers, one for a set that we want to project down to the squares. And again, we can do exactly the same compactness argument to get a structure that contains both of these sets. And actually, the compactness theorem isn't particularly picky about how many sets we try to throw in. We could, if we wanted to, throw in countably many sets, or even uncountably many sets, using this sort of technique. So let K be an arbitrary collection of sets of natural numbers. And we can do exactly the same compactness argument. Start with T, which is the set of all true sentences of weak S1S, and we're going to add in a constant symbol for every one of these subsets of the natural numbers. And onto T, we're going to add just a basic specification of whether or not N should be in CK, the element that we're going to want to project down to K when we restrict it to just the natural numbers. So again, K could be uncountable even, and this sort of construction will give us an uncountable T, but that's perfectly fine. We can toss that into the compactness theorem, and it will toss us back a non-standard model of weak S1S. Again, it's going to be some structure that satisfies T that contains elements manifesting all of these constants, satisfying all of these statements here. And those elements, given by those constants, CK, are going to wind up restricting down to the Ks that we wanted them to. Combining this construction here with the substructure lemma gives us a great deal of control over the restrictions of our non-standard models to just the standard part. What do the sets in our non-standard models look like when we restrict them to just the natural numbers? We could even say a few things about the first order parts of these models that we wind up getting by modifying our compactness construction to add in some first order constants and some additional statements requiring, when we require that they're true for all n, requiring that C be infinitely far away from 0, and that D be infinitely larger than C. And what these requirements will do is require the first order part to have these two elements that are infinitely far away from each other. In other words, it's going to have at least two different non-standard parts. Or in other words, it can't have just one non-standard Z part. That is to say, it can't be an omega plus Z model. And we can do all sorts of constructions like this to really force this non-standard part to become very large and unwieldy, which is really unfortunate. I'd actually like to force this non-standard part to become very small and wieldy. I'd ideally like my non-standard models to be an omega plus Z model. But regrettably, there's no way of just doing a compactness argument to require that. We can only force this to get larger by adding in new constants and requiring them to be infinitely far away from each other. So that brings up a really interesting question. What can we do in the case of omega plus Z models? What sorts of non-standard models of weak S1S have first order part omega plus Z? I'll talk about that in a future video, but first we're going to need to set up some more tools for constructing non-standard models of weak S1S. Specifically, I'd like to be able to cut up and paste together various non-standard models of weak S1S to produce new non-standard models of weak S1S. So thanks for watching. If there was something that wasn't clear to you, or if you have any questions, it would be really helpful for me to leave questions down below in the comments. And otherwise, I hope to see you in a future video.